Welcome everybody to Lecture 5, Information Retrieval in the now winter semester 22 and 23. Weather is not holding up. There is snow on the mountains and I can still hear you talking. Thank you. So I will say something about your experiences with the last exercise sheet, which was about compression, codes, entropy and beautiful mathematics. And today we will talk about a fuzzy search, and we have prepared a fascinating lecture for you with a lot of new material. It's this time there will be quite a bit of math, basic but beautiful mathematics in the lecture, but then there will be an algorithm and your task will be again to implement something, so I guess several of you will be happy with that. And we have also compiled a beautiful data set for you, and we will talk about that in a second. So about the feedback about the last exercise sheet. So the first exercise was about Lagrange again, so second time to practice it. Many of you liked that. You had more problems with exercise 2. And as usual, there's mixed feedback, so it was a mathematical sheet. Mathematics is cool because it's so hard in interesting ways. It's a matter of willingness. More time is helpful. Very complicated tasks, spend 4 days trying to solve it. So several people said that they spent a lot of time on exercise 2, which was about proving this inequality, which is why I have an extra slide where I want to show you something. Needed a lot of time to show this part. That's actually what my slide will be about. I hope there will be more coding sheets and less math. Yes. Then I made this comparison with the arithmetic expressions. That's of course correct if you have this arithmetic expression as I had it on the last sheet. It's basically you evaluate it even if it's complex. You evaluate a part, it becomes less complex, so it's strictly monotonic in that sense, whereas a math problem, it's a little more of a search. But I still argue that it's pretty mechanic. That's one of the points I want to make in 2 slides. And somebody said the exercise was more about math skills than about compression. That is true, but since many of you are still having trouble with the math skills, that's hard to avoid. This is already a simpler version of an exercise which we had several years ago. So yeah, you have to start wherever you are. So there was this question about your relationship with mathematics, and you gave super interesting answers. Many of you said something like this, that you actually like it a lot. Many of you, basically everybody said that, but you want to make more progress, and you wonder how you do that. More examples would be helpful. Many of you, so it was amazingly interesting what you wrote, so thank you very much for that. Many of you mentioned time as an important factor, so just needing more time for the exercises, for learning. Somebody even said time is really the only thing, no amount of explanation from me, or you just need time. Several of you wrote that you miss background, and I agree. Only few good teachers teach mathematical or taught in the past intuitively. My love for math increases. It got and gets better with practicing. Problems with logarithm rules, these were important for the exercise too. They feel so unintuitive. And yeah, that's what I said. So for me, very interesting bottom line was, many of you actually, so there's not so much of a, I don't like math, please skip it. It's like I really like it, but just wishing to have a better understanding and more time. Time. Let me not do the whole exercise too. I would love to show it to you, but time is limited. But I want to show you one thing which I feel might help some of you. So the task was to prove this. It was really, and of course the one who said that is right. I mean, you could just forget everything about compression and just prove a mathematical inequality, but you can say that about everything. Of course, it was implicitly part of the exercise to understand why you are proving that. I mean, this whole thing is showing that Golomb encoding is entropy optimal for a particular distribution, namely gap encoding, but that was kind of given to you, and then you had to show the math behind it. So it was like an expression, and you have to plug in stuff, and it looks a little bit ugly, but simple. I mean, it's something divided by something else. M was given, which is again, and then you have something rounded down. In the denominator, you have something rounded up, and so on. So I already wrote that in the forum, and I think several of you found that helpful, that you start by writing down and doing the obvious simplifications, like you have a ceiling, so rounding up or rounding down, and then you want less or equal, you can just drop the rounding down. I don't want to show that to you now. What I want to show, because several of you said that, and let me see whether that pen works. I didn't test it before, but I'm hopeful that it works. So at some point, so after the simple simplifications, the simple transformations, you end up with something like this. You have to show something like, and I have to write a little bit smaller so that I have, you have to show, where do I write it? Maybe I write it here. You have to show something like I minus 1 times P over ln2 less or equal than, and I think it was log 2, if it's wrong, and then you have 1 minus P over I minus 1. And if you did these simple things, and there was still this hint, so like a joker who wants to be a millionaire, for all x, you had this hint that 1 plus x is less or equal than e to the x. And many of you said, yeah, all fine, so what I wrote on the forum, yeah, I got there, I got to something like this, but I actually spent all my time here. And so the question is, how do you prove something like this? So you see this and you say, no way. I mean, what does the left side have to do with the right side? There's a p here, and here's the p in the logarithm. It just doesn't look right. And I want to show you two things. So I want to, a thinking process. And so let's first start on the left side. So the first thing is, and then I also want to show you a little bit about how to do this technically. So the first thing is, let's get to something from here to something we know. So maybe I write it again, but a little bit transformed. So I have this I minus 1 here times P over ln2. And what's very important now I'm just doing transformations, and I'm not showing that something implies something else. So this is what I'm showing here, not a proof. I don't know if I can do this. So not proof yet. So this is just derivations to get some intuition. And this is, I think, how you should do that. And the right-hand side then will be the proof. And I think it's important to differentiate between the two. So one thing you can do, okay, I minus 1 in the exponent of the logarithm. So many of you rightly said basic rules. You have to know if you have the exponent in a logarithm, then you can just put it in the front, right? So if you have something like log x to the y, it's y times log x. Of course, if you don't know that, then I agree it's hard, but that's what I would call basic arithmetic, especially in computer science, mathematics, right? These laws of logarithm, when you have logarithms, you have them all the time. So that already gives you the I minus 1 in the front, and then you have another thing is, if you have log to the basis of b of a, then it's just log of a divided by log of b. And again, I would call that basic arithmetic operations, like plus, minus, divide. You should just know that. If you don't know these things, I agree, then it's hard. So what are we having now? So now we are having I minus 1 comes to the front here. Let's just take the ln, because we also have the ln here. And then we have ln 1 minus 1 over p divided by ln 2. So by doing, I would say, rather obvious things, I mean the log 2, you have an ln here, so let's apply that rule, and just pulling the exponent to the front, you have this here. So now you have I minus 1 here, and I minus 1 here, and you just, okay, let's drop it, it's the same, that's fine, ln 2 here, ln 2 here. And now, so let's just continue. So now what do we have left? P ln 1 over 1 minus p. And very important, I'm not proving something here. I'm just transforming, so I'm on the left side to get somewhere something I know and see whether it works out that way. Many of you confusing are getting this idea for a proof with proving. I will come back to it at the end. Let's just do another transformation. Do the exponent, apply, take everything e to the power of. So this gives me 1 over 1 minus p. Okay, now let's take let's take 1 over 1 minus p, because you know you have that hint, and yeah, bingo, I would say. You're already there. It says 1 minus p, 1 plus x less or equal e to the x. Here it says 1 minus p. That's exactly this when you plug in minus p for x. So you arrived at something which you know. So it's like bingo here. Bingo. And I would say these are rather simple and also obvious transformations. And now the other thing which I wanted to show. Many of you, I see that a lot in what you submit, but also in exams, you write something like this, and I'm not even, maybe I write it and then I delete it again. Then sometimes you're writing this, or maybe this or something. Don't do that. This is not a proof. This is just getting the idea. I mean, you would have to be careful, very careful about whether this implies this or the other way around. Actually, you need the other direction, right? Because you're coming from a hint and you want to prove that. So when you do something like that, and that's very typical in this kind of mathematics, you have this here on the left-hand side to get some intuition, and now that you have it, now you can do the proof, and I do that on the right-hand side. So now I know, I should start with this. So let's start with this. So 1 over, and let's, so 1 minus p is less or equal than e to the minus p. And this is because of the hint. So we start with this. Yeah, we know this for all x, so it also holds for. And now we know, okay, this is, and now let me just do this the other way around. So it's e to the p is now less or equal than 1 over minus p. So this is just taking the reciprocals on both sides and then switching side. If I take, this becomes 1 over 1 minus p. Here the sign changes. And now I switched the sides, so I did two things in one here. And this is now an implication, right? I'm coming from here to here. Now I apply the logarithm, so let me just, so this is applying ln now of this, or maybe I should just write it on the other side. Yeah, so this is now, let me not write it, but just say it. 1 over, I'm applying ln to both sides. Can I do that? Yes, I can do that. So this is now, this implies this. This is now a proof. Now let me take it to the, let me multiply by I minus 1 on both sides. So this is I minus 1 times, and let me do two things at the same time here. This is like, if I put it in the log, it's like this. So it's just multiplying both sides by I minus 1. I can always do that. And now let me divide by ln 2. P times ln 2. And this is again equivalent transformation. Now it's ln this by ln 2. Let me also do two things at the same time. And it's now the log 2 minus p I minus 1, which is also bingo. And now I have even proved it. And this is, this was like the hard part of the proof. So, and it's interesting, so two things here. One, how do you get to something like this? Here's something where you wonder, does it really hold? Try some transformations, and I'm arguing you're applying here like a box, a sack of basic tricks, like maybe 20 tricks one can do the typical logarithm rules. And yes, it's a little bit of search, but I would argue it's not too much of a search. There's really not so much you can do here. Apply these tricks until you get to something you know, but then let me say that again, because it's so important. I see it so often. This is not a proof yet, right? This is just trying to get idea for the proof, and once you have this, now you can start from what you know and now check whether it's really going in the right direction. Is this an implication? Maybe you are dividing by 0 sometimes. This is the proof. This is just for getting the idea of the proof. Many of you, I see that a lot, are confusing this. If you write this, it's not yet the proof. It's just getting the idea. Arrows are missing here and so on. Though very often the proof is just this thing here in the other direction. Took a little bit of time, but I think it's super important. One more slide and maybe then opportunity for you to ask questions. So my feeling is, and I think it concurs with what many of you wrote, that it would help very many of you to develop these super basic practical skills, like these logarithm laws should be just as natural as multiplying or dividing or adding numbers. And it's not, let me say it again because it's so important, it's not that there are 1,000 of these rules or tricks. I think it's maybe, I don't know, 20, 50, it's a finite number and a small finite number. And my feeling is that in the math lectures, this is just taken for granted. That's a problem. It's assumed that you know that. Many of you have missed this somehow, and then you never have time to learn it, to learn these very basic things. And probably we would need a lecture in the curriculum which just does that. Practice this absolute basic stuff, because that's what many of you, I think, are missing. The basic stuff and also the practice with it. And actually, I also contend that math skills and programming skills are really very, very similar. If you have this basic, also programming is not so easy. You have a task. How do I do that? You have your basic toolbox, and now you're trying out a number of things, right? It's always a little bit of search, but not a huge search space. I mean, you have your 5 tricks and you try them out. And in math, here it's also like this. You have to prove this. You have your 10 tricks. You just apply them after one of them works. Not so different from programming, actually. And you also know when it works. You also have that feature. If you arrive at something which you know, in this case the hint, then it's like your program compiles. And of course, with more experience, and if you are super clever, then you can do it faster and more elegantly. That's also like in programming. If you're very experienced, then very quickly you can write down a program that works. But the important point is, in programming, as in math, with just trying out and enough time, you can always do it somehow. So, yeah, corollary, liking programming and liking math. So I think really the same thing, and your feedback kind of confirmed that. Okay, so that was a little more time than usual, but I think it was important. Is there any question or comment from your side? Yes, please.
Yes, so I completely agree with you that for me at least I need those basic practical skills, and I'm starting to learn what they are through these exercises. But how do I go from that to actually learning? Like, do you suggest any places where you can start practicing these skills, or is that something you would have to Google around and figure out yourself?
It's a very good question. Though the question is, where do you practice these? You're saying you are learning this as part of these exercises. I think there are enough. I don't have one specific pointer right now. I think there's enough sources or videos or I don't know what, where you can, all these, proving these little things. It's like really this basic, it's like doing calculations in your head. I think there are many places probably where you can do that. The limiting factor is probably time, right? Everybody is so stressed, you have to do your exercise sheet, so it would kind of take, okay, 5 hours per week or so, or 1 hour per week, I just do this, and I catch up with what I missed, because actually you should have learned this sometimes long ago or in the first semester, but you didn't, so I think many of you just need to catch up. And that's hard catching up because the daily life is so stressful. So I think what I learned from this, and what I try to do, and I already tried to do that a little bit in the past, is like sneak in some basic math stuff into my lectures. I mean, some of you then complain about it, you say it's not really information retrieval, and it's true, but I think many of you just need it. So just sneaking in like basic math exercises for you to prove this. I think that's a good way. So maybe it would be great to have a lecture, a whole course just about this in the curriculum, but there's no such course. Any other question or comment at this point? Yes, please.
Is the proof strategy for the constant equal to 1 the same as one we have seen?
The proof strategy for constant equal to 1?
Yeah, so there was this optional exercise to get the constant to 1.
Ah, that's hard. That's harder. Yeah, this is, I think, what changes when the mathematics becomes, what's hard about mathematics? It's a very good question. So the question was, there was the optional exercise, prove this plus 1. And it's not linear, right? It's not just plus 5 plus 1. It can become arbitrarily more hard if you do these little changes. And what is hardness in mathematics? I think by this example, one can explain it really well. This, I would say, is not too hard because the search space is small. You're given this, and there are like 10 obvious tricks which you can apply. You can basically try them one after the other in 2 different combinations, and then it will just work. And when it's harder, it means that the search space is larger, and you have to use something maybe unexpected, and that's what makes it hard, and that's where experience comes in. Like you have maybe 100 tricks which you could apply in different orders, and then combinatorial, it's a lot. And then it becomes like about knowing, oh, in this situation, this often helps, let me try this or that. So that's why the plus 1 thing is not easy, why it was really optional. The plus 1 is not easy because you have to, it's also still basic mathematics, and I don't have it in my cache right now, but it's not as easy as this. So if you are interested, I can post it somewhere. I think many years ago it was even the task to prove that, but with more hints. Any other question or comment about this very important topic? I would love to give just a lecture about this basic math stuff, and it's nice to hear that you like it. Just want to learn it better. Okay, so let's get on with the lecture. Probably will need a little longer today, but we will let me just, you can already think about that. Last question on this exercise sheet is, how stressed are you feeling? We are considering having no lecture on December 6th. That's 2 weeks from now. So you would then have 2 weeks, you would have a little more time to practice your math, and also another 2 weeks then to work on the exercise sheet from the week before. Let us know what you think, whether you think that's a good idea or a bad idea. Yeah. And so maybe we take a little longer today, and then we have a week off. Fuzzy search. So it's a super nice lecture today. More mathematics in the lecture, more practical in the sheet. I hope you like that. So the problem is, you're given, and let me show, we will also do maybe a little coding in the end, maybe not. We have this beautiful data set, which is linked on I've shown you Wikidata in the very first lecture, information retrieval in the winter semester. This one, data sets, Wikidata. Yeah, here's the data set. And what it is, there's a lot of information here. Maybe let me just cut the first column just and look at that. And it's it's entities from Wikidata. It starts with the countries, but it's basically everything, not everything, but many things you have a Wikipedia article about or Wikidata entity about. So here you have some dates, you have mobile phones, Scandinavia, some countries. So it's just, we will often call this words in the following, but it's just strings, right? So space is also a character. It's not important for now that this is 2 words. It's just a string and space is 1 character. So consider each of these as one thing, as 1 word, even if it's 2 words. And what we have quite a lot of these. Let's just look at how many by doing this with line numbers. So it's 2.6 million names of things. And what we want to have today, you type something and then you want to find matching names and you want to be able to make mistakes because that's very important. So the simplest form is you type something, frei, we will ignore case. You want to find Freiburg, prefix search. Maybe you are mistyping Breifurg, you want to find Freiburg. Very often you mistype, you don't know how exactly it's spelled. And the ultimate thing, and that will be the exercise sheet, you just type a prefix and you mistype in the prefix, so fuzzy prefix search. And that's what we will do today, which is a very cool feature which you basically want everywhere when you want to select something from a long list. You type Brei and you get Freiburg. That's what we want today. And you want it from this list of entities. Yeah, so you type something, you're looking for, I don't know, you're looking for Sapporo Maruyama Zoo and you type it with typos, just Sapporo with 1 P. You don't type everything and you find this. Okay. So we will solve these 2, fuzzy and fuzzy prefix. They will be very similar, and prefix search just a special case. If you can find something with typos, you also find the things without typos, just a special case. There will be 2 challenges, similar to as we had it in the beginning for keyword search. One is, what does it mean that something, why is this a good match? We have to define a similarity measure, Breifurg similar to Freiburg, and then we have to do this fast somehow. And this is just, so where do these dictionaries come from here? So one source is just you take, I don't know, you have your particular application, you want to select an entity from Wikidata, then it comes from that list. Another possible origin, you have a big text collection and you just you extract common phrases from there. And of course, what people search. You have a query search engine and you know what people search and you suggest from that. That's basically how Google does it, right? They know what people search, and when you type something, you get completions from that. And this is what we have here, a given list of entities. What's a simple solution? When you do more complicated stuff, it's always important to understand what's the trivial solution. Maybe it's good enough. Well, the trivial solution is what, we can actually do it. Let's just, I can do grab something here, let me do -I, -x, grab, and let me type, -I is case insensitive, Freiburg, and let me maybe take Breifurg, and let me say I'm allowed to make 2 mistakes. And now and I shouldn't have, okay, now I have to type it again. NFS teaching, information retrieval. Oh no, this is not, I think I should have, I just want the first column. There's more information in these files which you don't need for this exercise sheet. I will come back to that, so I really just want the first column. And also for this exercise sheet, you just want the first column. Let we just pipe this into agrep and see what I get. Okay, I have to install agrep. Agrep is a proximate grep, so find all lines in the so grep just finds you all lines matching a pattern. Agrep. Okay, I find Bleiburg, but no Freiburg. Interesting. So Freiburg is not an entity in there, probably because it's called im Breisgau or something like that. Let's try that. Yeah, now I find Freiburg im Breisgau. You see, it's actually not that bad. agrep is pretty fast, and it's not a huge list, but if you have a larger list, then this can be a problem. So agrep is a tool. All matching lines will be output. This means match the whole word. This means up to edit distance 2 minus x. Okay. So what's the time complexity? You're going through all the lines, and you have to do something for each line. You have to do a check. And you have to do a check with an algorithm, which I will show you next. It will take about 1 microsecond, I would say, to check. Depends on how exactly you do it, whether two words are similar up to 2 typos or something like this. So if you have, here's just some back of the envelope calculation that something like this is fine if you have a smaller set. If you have a larger set, you do need to do something more fancy. It's a bit unfair here, the comparison, because agrep is of course a program written in C. For the exercise sheet, you will do it in Python. If you would implement this with Python, it would take 10 seconds or 1 minute, I think. We already saw that huge performance difference. So yeah, this tool, this basic, just going through all the elements and for each of them checking, is it similar in Python, it would take very long, so would not be practical. And that's what all the lecture today is about, how to do this in a more clever way. And it's a very fundamental algorithm. First we have to talk about, and after this part we will have our break, similarity between two words. And here's a very fundamental measure introduced by Levenstein and also others already in 1965. There's always one name associated with these things, but actually, I mean, anyone could have come up with that at the time, but there's always somebody called the inventor. That's just how humans like it. They always want to associate individual with things, although the opposite is true, right? Everything we do is pretty collective. So the edit distance between two strings is getting from one word to the other with a sequence of the following 3 operations. And let me take we have a whole lecture about this in information, in algorithms and data structures. Here we'll just do this very quickly. So let's say I want to go from the word doof, let's say doof, to the word blöd. From doof to blöd, they are semantically similar, syntactically not so similar. And now you can do you have sequence of operations. You can replace a letter, you can insert a letter, you can delete a letter. So let's just do a sequence here. Let's just replace the first letter, so that would be a replace operation here. Replace, and I replace the first character by a B. I don't have to write down what I replace. And I think I left too little space here. I'm sorry, we want to go to blöd. I will write it down again in the end. Let's maybe add bloof. Just need a little more. So I'm replacing the second character and we want to get to blöd, blöd. So that's replacing it by an L. Now I need the E, and there are several ways to do it when you think about it. It's not a unique sequence, Now I'm inserting something at position 4. Insert. And what am I inserting? An E. And now I'm replacing the last character, and then I get where I wanted to get, and now I wanted to get to blöd. Yeah, and that's how the edit distance, no, it's not yet how it's defined. So now I have a sequence of 4 operations here. So now it's replacing the 5th character by B. And now important, just so that we are clear, this does not yet prove that the edit distance is 4. This proves that the edit distance is less or equal than 4. Maybe there's a sequence of 3 operations, right? I've just given you one with 4, so edit distance is 4 or less. We haven't proven, and it's actually not so easy to prove. That's what the next slides are about. This only shows less or equal to 4. X, Y, less or equal to 4. How do you prove that you can't do it better? So actually, in this case, the edit distance is 4, and not so easy to see. That's why I like that example. And it's also not so easy to prove. So as I said in the basic algorithms and data structure lecture, there is a whole lecture just about this and the theory behind it. For today, we just take that for granted, but I want to show it to you quickly because we need it, so you should understand the basics. A basic notation, when you talk about strings, you want to know, have something for the empty word, because if you just write nothing, then it's hard to understand whether it's nothing is written there or whether you mean nothing. So you have a symbol for it, epsilon. It's the empty word, nothing. Substrings are denoted by this notation here, so square brackets, and then from here to there. We're starting indexes with 1, so it's not 0-based, 1-based, just more intuitive, not how you would program it. Here's some simple properties, also popular exam questions, so when you prepare for the exam, think about this. And your question, practicing math things, proving something like this is also great. I always have a lot of these on the slides, little properties to prove. So proving formally that the edit distance is symmetric. Why is it symmetric? Let me ask you that. Why is the edit distance from x to y the same as the edit distance from y to x? Yes?
Because if you can transform one with another with a number of operations, you can always invert that by...
Yes. The answer was if you have a sequence going from one word to the other, you can invert the sequence, and every operation you can invert. Replace this character by that, has an inverse. Insertion becomes deletion, deletion becomes insertion. That's the intuition for the proof. Now it's nice practice to turn this into a proof. We are not doing that here. So behind each of these is a small little proof, a great way to prove mathematics. I'm not asking you here in the interest of time. The edit distance to the empty word is always the size of the longer word, because what can you do better than inserting one character after the other? Nothing. If you have two words and they have different size, one has size 5, one has size 8, you need at least 8 operations, because each operation can increase the string length by at most 1. Here's something more complicated. We don't look at the details right now. Here's a recursive formula, and the whole lecture I mentioned in algorithms and data structure is about this. We're not going to look at this formula. It's just on the slides for reference. And the proof is also not trivial. It's super interesting, whole lecture about it. Let's just do it together so that you see it. And that's something you should understand. For this lecture, you don't have to know how to prove this, but you should be able to compute it. And let me do that right now. So we want to get from, and how do we do it? From doof to blöd, and we do that by putting it into a table. like this, and you will understand in a second why. So we have this table here, and now I write some numbers here, and I will explain them to you. So here in the first row and the first column, I just write this. This was also written on the previous slide, and just to understand what it means, let me maybe use wonderful green here. So what this number means, it means what we see in this table is added distances between prefixes of the words. So this here is, this is my X, and this is my Y here. And so this is the added distance between the empty prefix of doof, so it's the added distance between epsilon, because I'm in the first row, so this row stands for the empty word, this row stands for D, this row stands for DO, this row stands for DOO. So if I go down here, I'm getting all the prefixes of doof. There are 5 of them, including the empty word. The word itself is also a prefix. It's just the whole word, and here I also have a 6. So this is the added distance between the empty word and blue. And this is why you have this trivial sequence of numbers. Empty word to something is just length of the word, right? The added distance is just 3, because what can you do apart from inserting one character after the other? It's obviously the best you can do. And now, applying the formula on the previous slide, which I didn't explain, let's just do it together here. What you have to do, now you fill in this table, one entry after the other. You look at the 3 neighboring entries, and you basically take the largest one, the smallest one, plus 1. That's basically what the recursive formula on the previous slide said. You take, these are like the entries just above, to the left, to the right, to the diagonal. You don't have to understand the details. And there's a little twist here if the 2 characters at the current position are equal. And we will come to that in a, So let's just do it together. We just apply it here, and while applying, I will explain it to you. Did I pick orange or red? That's the right color. Okay, so it's orange. So what I do here, I take these 3 entries, I take the smallest one plus 1, and I check whether these 2 letters are different. D and B are different. So here it's 1. And let's just do it for a while and then check an entry to see if it's correct. Here I have D and L. I take the smallest one. It's here 2 smallest one, 1. I take it plus 1. It's 2. The smallest one of these 3 is 2, plus 1 is 3. The smallest one of these is 3, plus 1 is 4. Now, if the D here I have a D and here I have a D, and in that case I don't have to add plus 1 to the diagonal. That's just how it works. So here I take this one, 4, and I don't have to add plus 1. That's the 4th case on the slide before. So actually here it's a 4. And let's just check here whether that value is correct. This value stands for the added distance between D and blöd. Blöd, the whole string, because it's in the last column. And is it 4? Yes, it's 4, because one character is already there, and I just insert the other 4. So let's quickly fill the rest of the table. So it's always taking, let me just say it once more, you're always looking at these 3. Up, left, diagonal. You take the smallest one plus 1, and if these characters are the same, then for the diagonal you don't have to take plus 1. That's the simple rule. Not so easy to prove, easy to apply. Here if 1 is the smallest, 2. Here if 1 is the smallest, plus 1 is 2. Here OO, they are the same, so I can take the diagonal if it's smaller than the others, plus 1. OE, the smallest one is 2, is 3, OD 4, and you tell me whether I'm doing something wrong. Maybe I now do it a little bit quicker. Here, 00, the same character, and there's a 2. So I can do 2 here, 3, and 4. And now, okay, here I have 4, 4. Here it's 3. Here it's 3. And now it's 4. Okay. And now, actually you don't want all these entries in the table, you just want the last one, but the last one is what you want, right? It's now the edit distance between the whole words. And what the recursive formula does is just give you how to define this by the edit distance between shorter strings, where at least one of the two is shorter. And what this also gives you, we don't need this here, it also gives you the sequence of operations, because you always know where you came from, where that minimum came from. And it even gives you multiple answers if you have many. And I think, let me just move this a little bit down, because it's more beautiful that way. And is there any question about this? Yes, please.
So,
yeah?
is edit distance defined as the minimum amount of operations required to go from one to the other, or just an amount?
It's the minimum amount to go from one to the other, because you can do, you can do it with a sequence of 100 transformations, replace here, back, something. It's the minimum number. Yes?
In the last line, third one, you have to choose 3, and then you have to add 1, and then you write 3.
For this entry here,
The next one.
this one,
Yeah.
it's 2 plus 1. If I take these 3, I take the smallest one of these 3 plus 1.
Okay,
So because of the 2, it's, I'm getting the 3 here. Okay. Yeah, it's tricky. It was a little bit fast. What you also see here is time and space complexity. You have to fill out this table, and it takes squared. It's quadratic, or a product of the length of the two strings. So it's not a trivial algorithm. Any other question about this? And what? In the chat. Thank you. It's highly related to what people do in bioinformatics. That's true. In bioinformatics, you also have it's strongly correlated in the algorithms. Data structure lectures, I actually explain it to alignment between two strings. When you want to align things so that the similar parts are below each other. So yes, it's very similar. You're right, and it's a very fundamental concept. You need it in bioinformatics for similarity between gene sequences. Prefix edit distance, that's what we are doing today. This is defined as, so here's an example, and let me do the example, let me explain it by example, and then we see how we compute it. First, what's the edit distance between these two words? Not prefix edit distance, but what we have seen before. What's the edit distance between uni and university? 7. I hear 7 several times, and that's correct. And why is it 7? Well, the first 3 letters are already fine, but then this is just 7 letters longer. And what can I do better than inserting these 7 letters? So it would even be simple to prove. So these words, from the perspective of edit distance, are actually not similar at all. They have a huge edit distance. But from the perspective of I type something and I want to find something, they are a perfect match, because one is a perfect prefix of the other. And what prefix edit distance does, it looks at all the prefixes of university. So I'm looking at U, UN, uni, univ, univ, univer, and so on. And now I'm probably getting a bit of trouble. And then for each of these prefixes, I check what's the edit distance to uni. And the smallest one is the prefix edit distance. So I look at U, UN, uni. let me maybe just write it here. So what I'm doing is I'm computing uni u, I'm computing uni un, I'm computing edit distance uni uni, I'm sorry, and so on. And I take the smallest of these. So what's the prefix edit distance between uni and university? Yeah, I hear a 0, and that's correct. It's a 0 because there is a prefix here, namely uni, where the prefix edit distance is 0. So prefix edit distance 0 means it's a perfect prefix. Here's another example. So somebody types univer, so they use a W, and there's university. First, what's the edit distance between these two? What do you think? 5, that's very correct. Yeah, we have 4 more letters, and you also have to replace the W by a V, and it looks like one cannot do better. So you see, computing the edit distance for simple words, you don't have to do the whole schema. You kind of see it. What's the prefix edit distance? 1. Okay, I see you got it. Very good. So you just take all the prefixes from this one, and maybe let me just remove this and just draw the prefix which gives you. So in this case, this gives you you take the edit distance for this prefix, and here you take the edit distance for this prefix, and then you get it. So yeah, this wasn't a feature. I think it started about 10 years ago or so that you had it, because it's not so easy to compute, but nowadays you don't want to miss it. And of course, very important, or note that this is not symmetric, right? The prefix edit distance from the other side is not the same. This definition is not. So note, let me just write it like this. In general, PED of X, it can happen, of course, but in general, it's not the same. Unlike the edit distance, which is, yeah, because it's about prefix, and prefix is not symmetric. When uni is a prefix of university, it doesn't mean that university is a prefix of uni.
Why don't we search the shorter words that we take the shorter words in front of? Because I think that's maybe the more intuitive way, that we look at the shorter words.
No, I don't agree. It's a good question, but when you think about our list here, then it's what was mentioned is, why don't we always take the shorter one first? But the thing is, there is an asymmetry in what you type and what you want to search. Maybe you are typing university and there's uni in the data set. I mean, it's okay, you could argue that you then also want to find uni, but that was a confusing example, but then you want to find it for another reason. There is what you type, and there is what you want to find. So I'm typing, I don't think if you are typing Vladimir Len, then you don't want to find things starting with V. I mean, you've already typed a lot, you want to find things which are longer than that. So it's just not symmetric in that way, right? What you have already typed, you want to, it wouldn't actually, if you type this far, or if you type Nelson already, you don't want to find everything that's starting with N, right? So it's really asymmetric. Do you agree, or?
I'm just thinking about it with the Freiburg and Breisgau. There would be, if in the list would only be Freiburg, and I would type in Freiburg and Breisgau.
Yeah, but that's where the confusion came from. In this case, it would be okay because you have 2 synonyms for a word, which is actually, it's a good way to mention, we're actually giving you more information here. Head -2, let me just give you, so in the first column, and that's good enough for the exercise sheet, you just have the names here, But here you also have all kinds of synonyms of these names, like the USA, America, the States. So these are also good matches. So in the Freiburg line, you would probably have Freiburg im Breisgau and Freiburg. But in general, not every prefix of a word is also a synonym, right? So for example, united just by itself is not a synonym. So it's really not symmetric. When you find a prefix, you want to find continuations, but when you want to find something longer, you don't want to match all prefixes. So, how do you compute the prefix edit distance? And let's say we have, you type, here's an example. Let's say you type Fibu, and maybe you want to find Freiburg. Let's say you want to compute the edit distance between the two. How do you do it? Well, let's do our schema. So let's write Fibu here, and I just, again, no proving here. But just let's write Freiburg here. Now, maybe I should put more spacing there so that it's less crowded when I put the number. And what we do is we use exactly the same schema, but we don't have to look at all the entries. So this first row and column is always like this for the reasons already mentioned. So it's 1, 2, 3, 4, 5, 6, 7, 8. And now let's just look at the last row. So the last row, so here we have Fibu to, the empty word is 4. Fibu to, what's the right entry here? So just from the definition and without knowing what the previous rows are. 3, yes, it's from Fibu to F. It's just the edit distance, not prefix edit distance. It's 3, yes. What's the entry here between Fibu and Fr? So let me just, before I ask these questions, so this is now, this is the edit distance between as in the picture before, between Fibu and F. Right? So it's just edit distance between prefixes. What's the number here?
3.
It's also 3, yes. And what's the number here?
3.
It's also 3, that's correct. Boring. What's the number here?
3.
I think so, yes. What's the number here? 4. It's between Fibu and Freib. Okay, I'm believing you. What's the number here? That's now, maybe we should write it down so that we see it. So this is now the edit distance between Fibu and Freibu. Fibu and Freibu. Yeah, it's just 2, right? Which is a bit, are you really sure? Then it's, the other one is 4 here. That is between Fibu and Freib. I think it's also 3, right? You see, even for short strings, it's not so easy. And this one is actually 2, right? Which is also interesting. So by adding more letters, you can become smaller. And so, yeah. PED of, I don't have to write this in red, I do it in blue. The PED is just the minimum of the last row, right? Because it gives you all the prefixes of Y. PED x, y is the minimum of the last row. So it's the minimum of the last row, and actually there's one other trick which is written here on the slide. You don't have to, and that's, I think this is now a straight line, and I'm arguing that you don't have to look, no need to look to the right of this if, let me just write it and then explain it. If you just wonder whether the prefix edit distance is 2 or less, then you don't have to look to the right of this line anymore. And think about it. Let me just write it down. To the right of this, if you don't want the exact number, but just want to know, and if PED of x, y is less or equal than 2. So that's a simple trick. I just wanted to mention it. If you're just wondering, FIBO to whatever the prefix here is less or equal than 2. After you are 2 longer than the prefix, you don't have to search anymore, because here for sure it will be 3 or more. Here it will be 4 or more, just because it's 3 letters longer, it's 4 letters longer. So if you just want to know, is it similar up to a certain degree, where similarity is this delta, you don't have to look beyond a certain point. So that's the prefix edit distance. Is there any question about prefix edit distance? Yes, please.
So, like, if we were to implement an algorithm, would an algorithm be able to calculate the last row before calculating the rows above?
No, that's a good question. So an algorithm cannot. We just did it by visual inspection. But no, you actually have to compute the whole thing until here, but you can omit the right part. So if you are just interested in this, so yes, you have to fill in the table. But, and this brings me to the last slide, and then we have a break. It would be a lovely exercise to implement this, but there's more work. Second part of the lecture is about that, so we give it to you. Of course, if you have fun with it, you can implement it yourself. And we actually provide 2 versions, one implemented in Python, one implemented in C. You can, if you have problems with the one, use the other. If you have problem with the C one is faster. You have to install something. You can also run PyPy3. I mentioned PyPy earlier. Then the Python one is about as fast as the C one, but maybe just pick whichever one of the 3 works best for you. This one with pure Python is quite slow. Then you see that edit distance is hard to compute. This one is fast. This one with PyPy is reasonably fast. Yes, you have a question? I just saw optical illusions. Okay. Any questions about this? So to continue now, you can for now, not forever, forget about the details, but you have to understand edit distance and prefix edit distance. We will just work with these concepts in the following. You don't have to understand for now how it's proven or how exactly it's computed. Just should be able to compute it in your head. So that's what we need for the second part. So let's just make a 5-minute break here, and then we continue with the second part. 5-minute break. So let's continue. The second part is really exciting. So nice mathematics. The mathematics will be on the slide. The sheet will be practical, so don't worry if you don't. Actually, it's easy to understand, I think, intuitively. It's very beautiful. Let's start. So what's the motivation for the second part? So let's maybe go to the to this grep thing again, what we had here. You just go through the list and you check for what we had here. So just so that it's clear what the baseline is. You have this, and let me show you this one. Yeah, I have my 2.6 million words. I type something, I go through the whole list, 2.6 million strings, and for each of them I compute, is the edit distance smaller than whatever I want? Maybe I say, just give me up to 2 mistakes. Edit distance, prefix edit distance. You have to compute it 2.6 million times. That's wasteful, and it's also sometimes just too slow. And so we want to do this faster, and here's a very nice way to do this. And the idea is to do it with qgrams. And what are qgrams? So first, intuitive idea and 2 examples. So do you think, and it's an intuitive question, so what is small, maybe 1 or 2, is the edit distance between Freiburg and Stuttgart small? What do you think? Is it small? It's not small. Why is it not small? How would you formulate it? Why is it not small? Without even computing it. Yeah?
The number of operations to go from one to the other is...
Okay, that's the number of operations, but why? You look at the string and your first intuition is it's not small. Why? Why would you say so? Yeah, they are so different, right? Everything is different. Freiburg, Stuttgart, they're very different, right? Now, without computing something, Freiburg and Breifurg, is the edit distance small in some sense? Yeah, it's the opposite now, because here it's Rei, here's Rei, Urk, yeah, they have similar parts. So the strings look similar, so probably the edit distance is small. What exactly is the edit distance? Not so easy. If I would have asked you what's the exact edit distance here, not so easy, right? Even for strings of length 8, because they have some letters in common, R, and so on. But just whether it's small or not. And this is what we're trying to make more precise now and turn into efficient, very beautiful algorithm. And actually, often like this, the mathematics, not so trivial, but also not complicated. The algorithm then is relatively simple. So, a qgram, let's start with an example. I have Freiburg, and the q is actually a natural number. So here we are talking about 3 grams. It's the index here in that definition. And it's just all substrings of length 3. So it's the first 3 letters. FRE is a qgram. So it's just a substring of length 3. And then the next REI, REI, IB, Ibu, Bur, Urk. So these are the 3 grams of Freiburg. How many of them are there? 1, 2, 3, 4, 5, 6. And it's an 8-letter word. So I have 3 grams for an 8-letter word. Important detail, you will wonder about that in your implementation. Is it a set or a multi-set? We want it to be a multi-set. So if you have something like Ababa, so here you have 3 grams. I hope that's correct. Yes, I think it is. So you have Aba, and then Bab, and then Aba again. So now are these 2 or 1, and we want to count it twice. So it's like a multi-set. If you have the same element several times, you record that you have it several times. That's important when you implement the algorithm. And you don't actually implement it as a set, so it will actually come natural that you do it that way, just in case you wonder. What's the number of qgrams of a string x in general? Here's some example. So it obviously depends on the length of the string and on the q. What's the formula? Look at the examples and think about it. So here, string length is 8. And you have 6 of them at 3 grams. So it's a formula involving the length of the string, x. What is it? Length minus q plus 1. I think that's correct, yes? So it's the length of the string minus q plus 1. And this is also something one would have to prove, but this is also a mathematic experience thing with, right? You know that it's linear. I mean, it's obviously linear in the size of the string. It's also linear in Q. And if it's linear, it's enough to do it for one example, right? You just have to figure out, oh, it's x minus q. You do it for one example, and then you know whether it's +1, nothing, -1, and so on. Okay, popular exam question, by the way, to do this. So we have established that. So, similar words have many q-grams in common. And here's a lemma, and before we prove the lemma, let's look at an example. Oh, I'm sorry for that. Wake up. Let's take a little bit longer strings, because it's... what's the edit distance between Freiburgerin and Breifurgerin? What was it? Yeah, it's 2, right? It's just 2 letters. I mean, they are swapped, but it doesn't matter. The F is replaced by a B. So the edit distance is 2. And right now we're just talking about edit distance. Prefix edit distance will become later, and it will actually be very similar. But for simplicity now, edit distance. Here, let's just look at 2 grams for a change. It's called q grams because the q is a parameter. You can take 3 grams, 2 grams, 5 grams. These are all the 2 grams. I hope you tell me whether I made a mistake. And these are all the 2 grams of Breifurgerin. So it's a little bit longer. So how many of them are there? Let's just check. How large is this set? Yes, please.
If Q is larger than a word, is this set empty? Or does the set?
Yeah, it's the empty set. If it's larger, then it's empty, but it will not happen for a reason we will see in there. Yes? What is it? 10? I think I also opt for 11, but yeah. One-off mistake, classical mistake in coding. So 11 2 grams for each, they are the same length. Let's just look at do we look at the similar ones or at most of them are actually equal, right? So let's just equal. If, bu, fu are not equal, so we have a lot of equal ones, right? These equal, this is equal, and let's underline the different ones. So this one does not occur here. They are different. If, bu, fu. And note something very interesting here, which is important for the intuition later. I've changed something here, the B into an F. It affects 2 grams, right? It affects 2, not just 1. Why 2? Because if it's 3 grams, one change would affect 3 grams, because it occurs in, it's like the 3 grams, it's like you have a window of 3 letters and you slide it over the word. So if you change 1 letter, it affects q grams. So in this case, 1 change of letter affect 2 grams. Why does this change here affect only 1 2 gram and not 2? Who can tell me that? Yeah? Yeah? Yeah, it's nothing before it. It's the first letter, so it's kind of special, right? And we will exploit that later, or we will do something about it. So in the beginning, it doesn't have to affect 2. It can also affect less if it's at the beginning or at the end. And now let's look at, we didn't actually look at what the lemma says. What is set difference here? So this is now, if I take the set on the top and I remove everything that's also in the set at the bottom. So it's set different. What remains? So then what remains are just the different ones, right? So what remains is R, I, B, and bu. So this is what set difference is about. And so the number of these is just 3. And what the lemma, so that's why I'm taking set difference here. So I'm just, I'm taking this set and maybe just a diagram. I think we will have if I have two sets here, A and B, so this is my set A, and this is my set B. This here is then the intersection, right? And this part here, this is A without B. So I'm removing the intersection. So actually A without B, and we will use that later, is A without, let me also write it, you can also write it like that. The size of A without B is actually the size of A, and you're removing the intersection. We will need that later, and I will have it again. I'm just already writing it here so that you can use to it. So it's just taking away the intersection. The intersection here is pretty big because they have a lot of 2 grams in common. I'm removing all these which also occur in Y here, and what I'm left with is just the one which are different, which were changed. And what this lemma says is, if 2 words are very similar, like these 2 long words are, then this different set is pretty small. So here it's 2 times 2, the added distance is 2. So it's indeed what the lemma says. That's what the lemma says, right? So this is what writing at the bottom. It's always a bit harder, I'm sorry. This is what the lemma says, and we already got an intuition why it's 3 and not 4, because the one change in the beginning actually affected only 2 grams, so that's why it's actually less. Yes, please?
I'm not sure why this lemma holds, because I'm
Haha.
thinking now about a very long word
Yeah?
that I split and I change the position of both.
Yeah.
And I don't know, because if it's very long, then it should get a very long added distance, because
Yes.
it deletes the beginning and at the end. But
It's a great, let me just translate what you said, and it's great that you're thinking about it, because you're getting, that way you get intuition. Let me just make an example out of what you said. You said something like this, so I have frei, maybe Bürgerin, and now I have a string where actually Urgerin Brei. Urgerin Brei. I don't think you're allowed to use that in Scrabble, but let's just take it. So Freiburgerin and Urgerin Brei. So you just took 2 parts of Y, that's what you say, instead of taking Freiburg and Breisgau, Breisgurg and Freigau, or something like this. And now, what's the added distance between these 2? It's huge, right? But they have a lot of 2 grams in common, because they still have similar parts. But now look at this lemma. That's fine, right? This here will still be small, but this is large now. So the lemma still holds. It's an inequality.
I changed the way.
Yeah, but of course, in your head you changed it around, but it's a very good question to ask, because it points at something. These 2 grams are not a perfect indicator, right? This just says, if the added distance is small, if they are similar, then this is small. These 2 sets are very similar. It's not the other way around. Here I have a lot of q grams in common, but they are very different in added distance. And that's a very important intuition. Yes, please.
What happens if we use symmetric difference set difference?
If we use symmetric set difference, and what's the question? Then a variant, if we take symmetric set difference, then actually we will do that in a second. We will exploit the symmetry in a second. So maybe just wait for it, and then if you still have a question, ask it again. Because the question here is, we could also take why x, why did we choose it in this direction and not in the other direction? It's a very valid question. We will come back to it. And I think we will come... first we have to prove this, then we will come back to this. Oh, there's a question, just to be clear. Set difference on multiset, that's also a very good detail question. Actually, for set difference in multiset, the counts are important. So you have it 3 times here, and you subtract it 2 times, 1 occurrence remains. So that would be the answer to that. You would just subtract the count. If I have boo, 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 and I subtract boo, boo, then I have 1 boo left. But actually it will come natural in your implementation. Just just pay attention to it, that you do it the right way. Now I've given you the intuition for this lemma, and now let's prove it. And let's go through the proof rather quickly, because it's not part of the exercise, but of course eventually you should understand it and be able to prove it yourself. So how does one prove it? Well, we've given the main intuition already. Let's say the edit distance is 1. And here's the explanation. So let's say I have Freiburg, and let's say Q is equal to 3. I have 3 grams. This is my string X, and my string Y is Freiburg. So now I've changed 1 letter, and well, how many 3 grams does it affect? We have already seen that it affects 3 grams, right? It affects this one, and this one. These are now different. So Eib becomes Ix, Ibu becomes Ixu, and Bur becomes Xur. So if I do 1 edit distance operation, and that's also true for insert or delete, it affects at most, can be less, that's why less or equal, Q 3 grams. And that's why we have this less or equal Q. And now, if you have K operations, it kind of multiplies by the number of operations, which looks natural. It's actually not trivial to prove. Let me just give you the idea. If you have a sequence of K operation, it means you can get from X to Y in K hops, where each of them is just 1 operation, so the base case. So what you have now is this lemma holds for each case. Now you have indices here, looks a bit little intimidating, but it's actually simple. So you just have all these intermediate strings. Think of the doof, blöd example, doof, boof, bloof, bloev, blöd. For each of them, this set difference from one to the other is just at most Q. And now you need to prove this beautiful theorem here. And let me just prove it to you. Let's prove it in the abstract, and then you can figure out yourself how it can be used to prove this lemma up there. But this is another nice example for now. Let's just forget everything above. Just look at this and let's try to prove it. That's again another nice way to practice mathematics. I have a sequence any sets now. And now I want to know the difference. I subtract the last one from the first one, and I compare it when I take these differences first to second, second to third, third to fourth, and so on, and I take the union of these. Let me just prove this very quickly in the abstract without understanding what it has to do with the above. So if I want to prove that something is a subset of something else, then I have to prove take any element from here, then it also has to be in here. It's the standard proof technique here. And since this is a union, I have to show I take any element from here, it has to be in one of these sets, then I'm fine. Let's just do that. So let's start with an X from here. So it's in here. And now let's look at this sequence of sets, and let me put this here. So I have A0, A1. I have A1 without, is it correct like this? A0, A1, A1, A2, A2, A3, and so on. And I'm wondering, is Now I'm confused myself. Ah, no, that was wrong. I'm sorry. Made a mistake in my thinking. I'm just looking at these sets like this. A1, A2, and so on. Let me also write A3 and AK. It's actually simpler. And now I'm wondering my X. In which of these is this? So my X is, I'm starting with A0. It's in A0, not in AK, but it's in A0. So it's in here. And now I'm looking for the first time that it's in this set, it's not in that set. So I know that it's not in here, right? My X is from, I'm sorry, it's from A0 and not in AK. So it's in here and then it's not in here. So at some point I will have for the first time that it's in here and not in here. That's just a, so that's a nice mathematical trick. So this means by the picture on the left that there will be an I where X is in AI, but X is not, or in AI minus 1, to pay attention to the indices, but X is not in the next one. This has to happen, right? It's in the first and not in the last, so somewhere here along this sequence it has to be in this one, but not in this one, not in the next one. Just by any combination of arrows and X's I can put here. Which means X is in A minus 1 without AI, which means X is, so it's in one of these here, which means it's in the union. AI minus 1 without the AI, which is what I wanted to prove. Okay, that's just, if you didn't fully follow it, it doesn't matter. It's just a very nice little proof. You can try it yourself at home. But I think the intuition is still easy enough. It's, if you have one change in a string affects at most q grams, and if you have k changes, it affects at most q times k grams. I think that's the very simple intuition of the proof. It's harder than expected to make it mathematically correct. And maybe one meta comment which I think is important. It's important not to confuse intuition with mathematical proof, right? What I said first, you can easily take this as a mathematical proof, like, okay, 1 q-gram affects, so I have this word effect, I put it in quotes, what exactly does it mean? You would have to prove it, and that this here is also, okay, now I do this k times in a row, so it's kind of k times q and not q. Maybe it's right, maybe it's not, you only find out when you actually do the math, because maybe it's something you missed, some small little detail, and I can tell you from experience with having done this like 1,000 times, there always, if you do the proof, then you find, oh, it's actually not true for this border case about which you didn't think. Because when you think intuitively, you always have an example in your mind or something. And then, yeah, so so this, what we see down here is not dispensable. It's not like, well, why isn't that the proof, this intuitive thing which I said initially? You have to do the proof to see if it really holds. Again, the similarity to coding, I contend, and I think it's just a fact, you have a complex piece of code, you don't write a unit test, it's not correct. For sure, it's not correct. And you see that when you start writing unit tests, then it's some input which you didn't think about and it fails on this. So this is like the equivalent of mathematical proving. The intuition, you just think about the general case. Okay, so we have proven this lemma, and now forget about the proof again. It was just a simple intuition that It's written up here. Similar words have many q-grams in common. Now, it says in common, but it talks about the set difference. Let's actually talk about in common, and that's what the next slide is about. So now let's talk about the intersection between the two. That's more like in common, right? So this is the q-grams of x, this is the q-grams of y, and this is the set they have in common. And here's an example. So if we take these two words from 2 slides ago, Freiburgerin and Breifurgerin, then let's go here. How many did they have in common? 1, 2, 3, 4, 5, 6, 7, 8. So they have 8 in common, right? So let's just put that number here. So this number was actually 8. See slide 20. That was 2 slides ago. And what this here says now, it's greater or equal to 7. And now you have this formula. Now all you have to find out, how does the intersection relate to the set difference? And we have, I've already shown it to you. I just show it again. I have 2 sets. So that's now Mengenlehre, set theory. You have set A and B. This here is the intersection between the two, and you can, it's visual proof, and this here, this thing here is now A without B, and you can see from there that the size of A without B is, you take all elements of A and you remove the elements in the intersection. All these, if you remove them or not, it doesn't matter, right? The ones which are not in A makes no difference. The ones you are actually removing is the ones from the intersection. And if you plug this in the previous lemma, and let's not spend too much time on this now, let's just take this formula for granted. But that connects to the comment asked earlier. If you take this lemma here, you can just swap x and y, right? If this is less or equal q times ed of xy, then the same is true if you put y here and x here, because ed xy and ed yx is the same thing. So you can actually apply the lemma twice. And if you apply the lemma twice, then once, so here I'm doing this, so this is in this direction and this is in this direction, both are true, and for both I can use this formula, and by that I get 2 inequalities and both of them hold, which is why I get the maximum here. Let's not go into the details now, it's just by symmetry you get actually 2 inequalities from the lemma, and it gives you a slightly stronger inequality now, so it helps your algorithm. Let's not go into the detail, let's just continue so that we see the algorithm. And now we have talked about the edit distance all the time. Let's also understand what's the difference for the prefix edit distance. Well, the difference for the prefix edit distance is, so that's what the lemma says for the prefix edit distance. Here's an example. And let's also not bother too much with the detail. Now I can apply the lemma only in one direction, and I can apply it only to a prefix of y. I don't know which one. Now it's not symmetric, right? That's important. And let me just write that here. Oh no, it's written here already, right? In general, the prefix edit distance is not symmetric, which is why here in this formula I have x and y, and I can take the maximum of the two. Here I just have x. And apart from that, it's very similar. And let's also not go into the details here. But it's a formula which you want to use for your algorithm. Back to the intuition. Similar words have many q-grams in common for ed and prefix edit distance. Let's turn that into an algorithm. And now, yeah, this was going into the details, not so easy, but now the algorithm is actually pretty easy again. So what I do, I've typed something, this is my X. Now I have my big dictionary. And now conceptually what I do, it's not what I will actually do, but conceptually, for each of these words I compute how many qgrams do X and Y have in common. And I wonder, is it above this threshold here, which I've seen on the previous slide? And if it's not, so if they don't have a lot of qgrams in common, this is what they say, then I know that the edit distance can't be small, right? They have very few qgrams in common, then I know that the edit distance cannot be small. And you have to check it out for yourself that this is actually the right direction. If they have many qgrams in common, I cannot be sure that the edit distance is small. This is the example we have seen, a very good comment earlier. Let me see it. Where was it on the slides? Just here was this Freiburgerin and Urgerin Brei. Many 2 grams in common, but they are actually not similar at all. So in this case, I have to check. So it's a one-sided test. I can exclude it. If there are few qgrams in common, then I don't have to compute the prefix edit distance. But if there are many in common, then I actually have to compute it. So what I'm doing this to save edit distance computations. And the algorithm for PED is just the same. I just use a different formula here on the right. So that's the algorithm. I just use this bound. I compute the number of common qgrams. And then if it's very few, I don't have to check. If it's few, I have to compute the prefix edit distance. This is also important for the exercise sheet. You will actually pad the strings. We will just add, so if we have 3 grams, we will add $$ to both sides. And this gives the same result, because if I'm now doing edit distance with this string or with these strings where I have $$ in both sides, it's the same thing. And for the prefix edit distance, I do the same thing, but I'm just adding dollars to one side. I can't add them to 2 sides, because otherwise the prefix edit distance is not the same, because I'm taking prefixes of the words on the left side. So you will add this padding. And now so how do you actually implement it? That's the last slides now. And I need to take a sip. And we are a little over time already. So, instead of, yeah, we should get to an end because my voice is failing, I'm sorry. And it's cold in here, at least I'm freezing. We have now reduced, I should use sign language, we have now reduced the problem of computing the edit distance for 2.6 million strings to computing common qgrams on 2.6 million strings. This doesn't really look simpler, but actually it is by the following trick. How do we do that efficiently? Now we can use something which we already have, and this is a very beautiful connection to what we have already seen. We compute the following index, and it's called a qgram index. That's like an inverted index, but the things which matter now are not words in documents, but qgrams and words. So here I have an inverted list for a qgram, and I have incorporated the padding here. So that's the 3 gram $FR, and what's in the list is all the words matching that qgram. And because there's a dollar, it's all the words starting with FR. And here I've just taken words which are names of towns. So I have an inverted list for, and you can use the exact same code from lecture 1 I wanted to do it together with you now, but for reasons of time I will not. Anyway, it's the first part of the first exercise to just compute an inverted index for qgram. It's almost the same code. This is the inverted list for Ibu. It's all the words in your dictionary which contain the 3 gram Ibu anywhere. Chichibu, Freiburg, Ibuzuki, Malibu. As usual, you will not store, like we did for the inverted list in lecture 1, you will not store the whole documents or words here, but just IDs. So it's just like the inverted index we have seen in lecture 1, except that now these are not documents but words, and words IDs, these are not words, these are 3 grams. Yeah, I wanted to do this together with you, but in the interest of time I will not. Anyway, it's part of the exercise sheet. How do we use that index? It's actually I will show it to you by an example, and then that's the last slide. Oh, my voice is failing. So let's say the user has typed Brei, and we will do prefix edit distance, and we are interested in matches where the prefix edit distance is at most 1. So similar things, and we can make one mistake, deletion, insertion, and so on. So what I'm doing is I'm padding to the left with this dollar. This was this one trick. It doesn't change anything, but it gives me more 3 grams. It helps my algorithm to be more efficient. And now I take 2 grams here, for example, so I have 4 2 grams. $B, BR, RE, and I. And now I get the following list. And this slide will make it very clear how the algorithm works. So now I have the inverted list for this 2 gram $B, which is also in what I typed. And what does it contain? It contains all the words which start with B. Bangalore, Beijing, Berlin. I also have here the 2 gram BR. And here I have my inverted list, all the words in my 2.6 billion which have BR in them. Brisbane, Brussels, Gibraltar, it doesn't have to be at the beginning. RE, I have RE here. Bangalore again. Freiburg, RE. Singapore, RE. I have Beijing, Freiburg, Marseille. They are not similar at all, right? These are just inverted lists. Point is, I have typed this, I have these 2 grams, I only have to look at these words. I can ignore all other words because they have no 2 grams in common with my X. I know that the set of Q grams in common is 0. So I can exclude, especially if I type a lot of words. I don't even have to look at them any further. I know they have 0 programs in common, so they won't be similar. If I now take my bound from the corollary, we don't have to look at the details now. The bound will tell me if I want a word where the prefix edit distance is at most 1, it must have 2 grams in common. So I will now compute the union of these lists, and you have already done computing the union of lists. And now you just check, and while you do the union for each word, you count how often. So it's a variant of the union. Maybe you already implemented that, depends on your implementation for exercise sheet 2. You just count how often each word occurs. And which words occur twice here? It's Bangalore. Why? Because it shares 2 grams with X. Beijing, because it shares 2 grams with X. And Freiburg. Only these 2 have 2 grams, and by our lemma we know that we don't have to look at the others because they don't have enough 2 grams in common with my X. So these 3 are left, but I'm not done. That's the one-sided thing. I know one-sided in the sense all the other words, I don't have to look at them anymore. There's no way the prefix edit distance can be 1 or less. For these, I have to check, It's not guaranteed yet that the prefix edit distance less than 1. And here we have an example, I obviously did it on purpose, where you share 2 grams, but the prefix edit distance is actually pretty large. Why is that? Because the RE q-gram appears at the end here at BR. It starts with B, but the RE comes at the end. Just because you have 2 grams in common doesn't mean you are similar. So now I have to go for these 3 words. I actually have to do this pretty expensive dynamic programming thing with a table, which we have seen, which is an expensive calculation. I only have to do it for 3 words in this example. For all the other words, I've already excluded them. And let's do it for these 3, and that's our last deed for today. What's the prefix edit distance between Brai and Bangalore? What's the prefix edit distance? 7. Are there other opinions? It's prefix edit distance? Prefix. So you have to take all prefixes of the second word and take the one which gives you the smallest edit distance. 0? You only have to take the prefixes of the second one, not the first one. Other bets? I know it's late, but it's the last slide. 3. I hear the number 3, and that's correct. It's the number 3, and it's actually this prefix here, right? So it's bang. Brai and bang, you can't get any better. You get an edit distance of 3. So out of the race, no match. Right? So no match. It had 2 grams in common, but when we actually compute the edit distance, prefix edit distance is too large. Brai and Beijing, and it's the last thing I promised, then we're done. What is it? 1. I agree. So that's a match. 1, and what's the prefix? The prefix, it's Bei. Yeah, why not take Bei? It's the 3. Bei and Brai, it's just the R missing. So that's a match. If we type Brai, we expect to get a match for Beijing. Maybe we just mistyped the R. So that's a match. And the last one, 1. That's correct. It's 1, and the prefix is just frei. In this case, right, the engine does not know what I mistyped. So it's actually, frei. And that's another match. So that's the algorithm, and you see how everything came together. We had to do all this beautiful theory to get these bounds here. In the end, we can just use them without understanding, but then it gives us this, and then we have just few candidates to check. There we do the expensive computation, then we are done. Yes, please?
I think when we're constructing the inverted index of the q-grams, we're using a regular set because we do not pay attention to how many times the q-gram occurs, but all our proofs were for the multisets. So isn't this a problem?
Yeah, that's very true. So the comment was multiset or not. And the thing is, I think what you have to do, all you have to do, and this is actually it's the simplest algorithm from lecture 1. If a word occurs RE twice, you need to have it twice in the list. And then you have satisfied this. Because what you want in the end when you compute the union, you want to know how many q-grams from this list does it contain. So if you have, I don't know, RE, I can't come up with, if you have RE twice in your entity name or in your word, you would have it twice in that list here. But you can just do that. And not only that, if you implement it, it even happens naturally. You would have to do something for it not to happen. Like in the very first lecture, if you remember, if a document contained a word 3 times, it would just appear in the list 3 times if you don't do anything. Very good question, just pay attention to it, but I contend that if you do the natural thing, then you don't have to do something for it to be right, but just... And of course, here's the sheet. It's a long sheet, but it's only long because we're giving very detailed instructions on how to do it. And also there are unit tests which help you to see whether you really did it correct. So it's just the algorithm, it's all in individual parts, and then you do it. And it's a very beautiful algorithm and very useful in the end. You do this little search engine, like in the beginning, you type a word and then you get matches. Sorry for the overtime, but maybe we have a week off in 2 weeks. Is there any other question for now? Okay, now we go to our heated homes. Have fun with the sheet. See you next week. Bye.